In this video, we are going to introduce estimators and learn about its bias in particular. In the problems we study, the parameters of the distributions are usually unknown. For example, in the normal distribution, its mean mu and variance sigma squared are usually unknown, and in the Bernoulli distribution, its parameter p, which represents the probability of success in a trial, is also usually unknown. Therefore, we come up with estimators denoted by theta hat to estimate the unknown parameter theta. A way to compare between estimators is by their bias, variance, and mean squared error. Bias is the difference between the average value of the estimator and its true value, and the formula is shown below. Let's see a few examples to compare. Example 1. Let x be from a binomial distribution with parameters n and p. Calculate the bias of p hat being the mean of x. So p hat is the estimator of p, and we use the bias formula to get that the bias is equal to the expectation of x bar minus p, and since x bar is x divided by n, and the expectation of x is n times p, we get the bias equals 0 after the computation. Since the bias of p hat is 0, we call p hat a biased estimator. Let's go on to the next example. x1 to xn are from an independent and identically distributed Poisson distribution with parameter lambda. Calculate the bias of lambda hat equals to x1 plus xn divided by 2. Again, with the same formula, we have bias equal to the expectation of the estimator lambda hat minus lambda. By the properties of expectation, the expectation of x1 and xn can be separated into the expectation of x1 plus the expectation of xn. Since the expectation of any x is lambda, we have the bias equal to 0, and lambda hat is therefore an unbiased estimator. Let's move on to the last example. Consider x1 to xn from an independent and identically distributed normal distribution with mean mu and variance sigma squared, and let an estimator for mu hat, be the weighted average of xi from x1 through xn with their respective weights equal to I. A more colloquial explanation is 1 times x1 plus 2 times x2 plus 3 times x3 plus plus n times xn divided by n. Plugging in the same formula and with the expectation of any x equal to mu, we have the bias equal to n times n plus 1 divided by 2 times over n times mu, because of the fact that the sum of 1 through n is n times n plus 1 over 2. After simplification, we get the bias as mu times n minus 1 over 2, and since it is not 0, mu hat is a biased estimator.